So today I am going to be explaining how to derive a differential equation for the dynamical liquid level inside of a conical tank. So if we draw our conical tank, we're going to see that there is some cross-sectional area at the top, and we're going to call this AC. And there is also some cross-sectional area at the bottom, and I'm going to call this AB. So the cross-sectional areas are a function of height, the height of the liquid inside of the tank. So we also have a flow in, and we're going to call this Q in, and we have a flow out, we're going to call this Q out. So if we think about this system, we can apply the Bernoulli's equation. So at the level of the liquid inside of the tank is going to be potential energy, and then with the flow coming out, there's going to be kinetic energy. So if we think about this as a steady state system, which meaning that the flow in and the flow out have not changed in a very long time, we can consider that the height is going to stay about the same. Now, this height is descriptive of our flow in equaling our flow out. So where that height is sitting is where our flow in minus our flow in and our flow out are equal to each other. So now if we try to do a mass balance on this system, we're going to see that it's just density times volume. And if we have the same liquid inside of this tank, the density is going to stay the same throughout the entire tank. So we can just look at this as a volumetric balance. So the liquid volume inside of our tank is going to change with time. So we can have the change in volume over the change in time. And now the reason why the volume changes is because of our flow rate in compared to our flow rate out. So we can write the dV over dt is equal to the flow rate in, or Q in, minus the flow rate out, or Q out. So now if we start looking at the Bernoulli's equation for this dynamical system, we know that eventually our potential energy at some height h is going to be equal to our kinetic energy that is leaving our tank. So we need to have an equation for both the potential and the kinetic energy of this dynamical system. So per unit mass, the potential energy at some height h in our tank is going to be G times h. And now per unit mass, the kinetic energy leaving our tank is going to be V squared over 2. So now we can find our flow rate out from these two equations. So we can have V out is equal to the square root of 2GH. So now we need to figure out how volume changes with time. So we can have volume is equal to the integral of AC times the change in height. So we know that inside of our tank, our cross-sectional area does change with height. That's why we're writing AC times the change in height. So since AC changes with height, we need to evaluate our integral from 0 to some height h. So now, what is the derivative of volume compared to the change in height? So we can write that the derivative of the the change in the volume over the change in the height. We're trying to compare these two. But actually, the height changes with time, so we need to compare that also. So we need to have the change in height divided by the change in time. So now if we look at this system graphically, we have AC on our y-axis, we have H on our x-axis. So we know that the cross-sectional area and the height increase with each other. So our graph will look something like this. So the volume can be represented by all of the area underneath the curve. So the derivative of the volume will actually be this small slice right here. Now this shows how our volume is increasing as our height is increasing. And actually this small slice right here, as we can see, is AC. So we can say that the change in volume over the change in height is actually our cross-sectional area. So now if we try to combine all of these equations, we can notice that AC is equal to dV over dH. So we can write that AC times dH over dt is equal to Q in minus Q out. And this is coming from the first equation that we wrote all the way up here. So now we found a equation for our flow out right here. Our V out is the same thing as our flow out here. So we can write AC dH over dt is equal to Q in minus the square root of 2GH. So now we want to isolate our derivative of our dependent variable that changes with some independent variable. So we can have dH over dt is equal to, dH over dt is equal to our Qn minus 2GH, or the square root of 2GH, and then all of this will be divided by our cross-sectional area. Okay, so now we are ready to plug all of our equations into Colab and find a numerical value for our dynamical system. So we are going to start off by initializing and adding our NumPy, Plotly, and our solve IBP. And then we are going to initialize all of our starting values that we were given in our problem statement. So our H total is 8 meters, our radius at the top is 5 meters, our radius at the bottom is 1 meter, and then our cross-sectional area at the bottom, we're going to call this AB, is equal to 0.01 meters cubed. And our initial Qn at steady state, so this is going to be our Qn naught, is 0.1 meters cubed per second. The total time we are going to run our system for is 5,000 seconds. And I am just going to make a note to myself that Qn is going to be increased by 20%. Okay, so now we are ready to initialize the right-hand side of our equation. So we can define the right-hand side, and then the right-hand side has to do with the time and the height, so we have to include those. And now we need to return the right-hand side of our equation. So we return Qn minus 2 times G times H, and this section will be raised to the 0.5 power, or taking the square root of it, and we divide all of this by AC. Okay, now we need to define our H naught of our system. So we can define our H naught as being our Qn naught divided by our cross-sectional area at the bottom. And we are going to square this section, and then we are going to divide by 2 times G. Okay, so then we need to initialize our value of AC in the conical tank. So, oh, we got an error. Oh, we didn't put our G value in, so G is equal to 9.81 second, I believe. See if we can find this. Meters per second squared. And the value is, I want to make sure that I have it correct, 9.8 meters per second squared. So let's flip these around. Now we have initialized our G. Okay, so now we need to initialize our AC for our system. And when we look at our AC, we know that it changes with time, and the radius also changes. So to define our conical AC, we need to have our H total, or sorry, let's just put our H and then our H total, our radius at the top, and our radius at the bottom. Now we already know our H total that was given to us, our R at the top and our R at the bottom were both given to us, so now we need to find the actual value of our AC. So now to find the actual value of AC, we need to find the relative slope of the height compared to the radii. So we are going to draw a graph, and we're going to go from our R bottom to our R top on our y-axis, and then our x-axis is going to be the show of our height. So we're going to have height, and we're going to go to sum height total. So when our height is 0, we're at our R bottom, and when we're at our height total, we're at our, this is supposed to be R top. So when we're at our height total, we're at our R top. So our slope of this line is going to go straight through both of these points. And then we can write the slope of this equation. So the slope of this equation is going to be R is equal to R top minus R bottom. And this is going to be divided by our H total, multiplied by our height at some point, and then we are going to add our bottom back on. Okay, so now we are ready to find the slope of our equation that we just found on our whiteboard. So we can initialize R is equal to R top minus R bottom. This will be divided by our H total. I'm going to add one more parenthesis in here to make sure we have the correct syntax. We are going to multiply by H, and then we are going to add our bottom. Okay, so now we can return our area. So return numpy. So we're going to return pi times r squared. And now we are going to calculate our AC. So we now have initialized our conical AC value. So now we can initialize our actual AC to be equal to conical underscore AC times 8, well, in the parentheses H total, RT, and RV. So now, given in our original problem statement, we know that our Qn is going to, we know that our Qn is going to be increased by 20%. So we can say that our Qn is equal to Qn naught times 1.2, or 120, a 20% increase. So now we can use solve IVP to actually solve this equation. So we need solve underscore IVP, and we are solving the right hand side of our equation. we need to solve our right-hand side from 0 times 0 into our time end, which is 5,000 seconds that was given to us in our problem statement. And then we need to initialize our dependent variable. So our dependent variable is h naught. So we have to put h naught into brackets because solve IVP wants to solve multiple differential equations at the same time. So since we are only solving one differential equation, we have to try kind of trick IVP into telling it that our h naught is an array. Oh, we got an error. So conical underscore AC is not defined. Let's run this part. Let's run all of them again and see if that fixes it. Oh, I spelled it wrong. Oopsies. I think I spelled it wrong initially. That's okay. So give this a second to load. So our solve IVP did work, and this is giving us our our height value for all of these different times. Okay, so now we want to be able to find the height at any time. Actually, we have invalid value in our return term. Oh. We need to multiply this by our cross-sectional area at the bottom. Okay, so now our solve IVP is working good. So we are actually interested in this solve value right here. So let us, or no, you know what? So we want to be able to find our height at any specific time. So we need to say that our dense output is equal to true. So by doing this, we create a function that we can pull at any specific time. And now to look at our solve value, we need to set our solve IVP equal to a variable. So let's use result. Let's run this, and now we can do result dot solve, and let's evaluate it after 2 seconds. And then by putting 0 in brackets, we can actually tell solve IVP that we just want one singular value instead of an array of values. Okay, so here's our result. So this is our height after 2 seconds. So now we can plot this function. So if we take plot is equal to linspace. So we have to say that we want to run our plot from 0 seconds to our time end, and we want 100 data points. So now we have to initialize our h value, and this is going to be our result dot solve tplot, and then 0 in brackets. So now we should be able to look at our times that we're going to plot. So this gives us an array of 100 times, since we told it that we wanted 100 data points. And now we can look at our h value, and this will show us all of the heights at those times that we just pulled up. So now if we turn this actually into a graph, we can use fig is equal to make subplots, and then our x will always be equal to tplot, and we are going to set our y equal to our height. Let's put our width at 600, and let's put our height at 400. And then the plotly dark just makes it a dark graph instead of bright white. So let's let this run. So now we can see that our tank starts down here, and we slowly go up by that 20% increase until we slowly start to become straight. So let's see if we set our time equal to 10,000 seconds, and let's run all. Give it a second to load. So we can see that it starts to get straighter and straighter as we go. So let's increase our time a little bit more. Let's do 20. So we can see that we are almost getting to a steady state at this point. So in this problem, I explained how to derive the differential equation for a dynamical liquid level in a conical tank. Thanks for watching.